Hello folks, and welcome back to Physics with Captain Rod here. So I'm making this video to demonstrate how to apply Newton's laws on a problem where friction is a relevant factor. So, imagine we've got this incline here, 25 degrees of the horizontal. We've got this box of peaches or something sitting up here that's going to presumably slide down this incline a distance of 4 meters to the bottom. We're going to try to calculate how long it would take given the following frictional coefficients of 0.1 and 0.15. Now, just a little reminder here about frictional coefficients. They come in two types. You've got static frictional coefficients and kinetic or sliding frictional coefficients of friction. And the sliding friction is always less than the static friction. So this is the sliding frictional coefficient. This is the static frictional coefficient. So we're going to start this with a free body diagram. And the first force I always put in my free bodies is the gravitational force. We know that that's straight down, equal to mg. Right. Surface in contact. Again, that surface that's right here. Right here we have a surface in contact. That's going to give us two different possible types of forces. One that's going to be there for sure is a normal force that's going to point this way. No doubt that's going to be there. And because we have friction in this problem, we're also going to have a frictional force along the surface, which will have to be in that direction. So these are the three relevant forces here. I'm going to go ahead and talk geometry here. So here's a 25-degree angle. Now if you look at the following triangle here, just kind of imagine this triangle right here. If this is 25 degrees, this would have to be 65 degrees. But the normal makes a right angle to the surface. That makes this angle 90, which makes the angle between this normal and the mg 25 degrees. So I'm going to go ahead and get rid of these. Oops, there we go. Get rid of the red stuff here and go ahead and just label this 25-degree angle. Now, when dealing with Newton's laws and acceleration, forces and accelerations are vector quantities. We always have to define a coordinate system. One possible coordinate system to draw might look something like this, maybe x, y. However, kind of thinking ahead, this mg is parallel to the y-axis, that's no problem. But both the normal and the frictional force would have to be broken into components. And if this thing's accelerating, you'd have to break the acceleration vector into components. So long story short, that's just not a real great coordinate system to use for a problem like this. I always recommend this. Identify the acceleration direction, call that positive, meaning put one of the axes in the direction of acceleration. If this thing is going to accelerate, the only possible direction is down the incline. So I'm going to go ahead and put x this way, y this way. And again, it doesn't, oops, let me redo that here. X, y. So now, the normal force is parallel to the y direction. Frictional force parallel to the x direction. Only the mg has to be broken into components. I'm going to go ahead and do that right now. I'm going to draw those components in red. Right, so the mg, in place of the mg, we're going to think of this as a component this way and a component this way. Right? I would call that mgx because it's the x component of mg, and this one right here I would call that mgy. Now the mgx is opposite the 25-degree angle, so it's going to equal mg sine 25. And the mgy is adjacent to the 25-degree angle, so it's going to equal mg cosine 25. So we've got a lot of the work done here. We've got our free body done. Got a coordinate system written out. We've got the mg broken into components. Now we can start writing force equations. But before we do, thinking ahead, we're going to be dealing with the frictional force. And the frictional force can be written as the coefficient of friction times the normal. So before we move ahead, we've got to consider this thing right here, frictional coefficient. Well, before we can write any equations, we should decide if either of these are even relevant. Here's some possibilities here. It's conceivable that maybe this box isn't going anywhere. It's conceivable that there's just enough friction there to keep it from accelerating down the incline. So we're going to do some quick calculations here to kind of decide whether or not it's actually going to accelerate. So if I think of this kind of qualitatively here of what's doing what here, The force that's trying to accelerate this thing down the incline is this one right here. the mg sine theta. And the force that's basically trying to hold it there is this one, frictional force. So I'm going to go ahead and calculate these values and just do a quick comparison here. So when dealing with friction, we're definitely going to need the normal force, right? Because the frictional force is equal to coefficient of friction times the normal. So the first equation I'm going to write is this: sum of all forces in the y direction equals 0, calling up and left the positive y direction. Now, in general, Newton's second law is F equals ma. However, this box cannot be accelerating in the y direction. If it were, it would jump right off the incline, and I can, by observation, that's not going to happen. So there's no acceleration in the y direction, so net force in the y direction is 0. So looking at my free body, the normal force is in the y direction, so I'm going to put plus n. This component right here of the gravitational force, the mg cosine 25, is in the minus y direction, so minus mg cosine 25. Okay. The frictional force does not have a y component, and there's no other forces acting. So this is basically done. Net force equals 0, so the normal force is equal to mg cosine 25 degrees. All right, now, again, getting back to whether or not this thing's going to slide down the incline or not. Again, conceivably, there's enough friction to keep this thing in place. The force trying to accelerate this down the incline is this guy, the mg sine 25. And I don't have a mass in this problem, but I do know the g and the 25. And if I go ahead and run 9.8 times sine of 25, I get this to be about 4.1 times the mass, whatever the mass is. And I'm just going to do that. I'm just going to compare that now against the maximum possible frictional force. The maximum possible frictional force is going to be the static coefficient of friction, 0.15, times the normal, which we just found to be mg cosine 25. And if we calculate 0.15 g cosine 25, I'll go ahead and do this for just a moment. Okay, I get that F max is approximately 1.34 times m, whatever m is. Now, I don't have a number here, so I can't get a definitive number for F max, but I can do a quick comparison here. 1.34 m, 4.1 m. Obviously, 4.1 m is larger than 1.34 m. That guarantees this is going to slide down the incline. That also means that the sliding frictional coefficient will be the relevant one. So I'm going to go ahead and get rid of a few things I don't need here anymore. Alright. Now we know enough here to write our force equation, x direction here. Don't really need that either, but so let's see. Sum of all forces, x direction equals ma, calling down and left the positive x direction. Again, my standard rule of thumb is identify the acceleration direction, call that positive. All right, so if we do so, let's see. This force is in the positive x direction, magnitude mg sine 25. Minus the frictional force. Now the frictional force can be written coefficient of friction times the normal, which I know to be mg cosine 25. So again, this is minus F basically, and the frictional force is equal to 0.1 times the normal, and the normal is equal to mg. Right? Now looking at the free body, we've got the mg sine 25 minus F equals ma. And you'll notice that the mass cancels. It's the same mass everywhere. So the acceleration of this mass should be around, let's see, g sine 25 minus 0.1 g times cosine 25. I'm going to just pause this for a moment here and calculate a value.